You clicked this video because you are tired of expensive factory controllers that lock your hardware choices. You know the pain of cabling spaghetti in dense mobile robotics fleets where every new sensor or motor driver requires rewiring half the system. By the end of this explanation, you will understand how a tiny custom controller built on open standards can eliminate vendor lock-in while reducing wiring complexity by up to 80% compared to traditional point-to-point designs. The problem starts with the rigid architecture of most industrial automation stacks. When an engineer buys a proprietary zone controller, they are not just buying hardware, they are signing a contract that ties their entire system design to a single vendor's ecosystem. If you need to swap out a motor driver or upgrade a sensor array in 3 years, you often cannot do it without expensive firmware licenses or physical reconfiguration of the control logic. This rigidity creates massive friction when trying to adapt production lines to changing floor layouts or fluctuating robot densities. The result is a system that works perfectly on day one, but becomes a liability as soon as operational requirements shift even slightly. Consider how standard factory systems handle communication between zones and robots. They typically rely on point-to-point wiring where every single endpoint connects directly back to a central controller through its own dedicated cable run. In a dense warehouse environment with dozens of autonomous mobile robots, this approach creates what engineers call cabling spaghetti. The sheer volume of twisted pairs running along the floor becomes unmanageable quickly. It is not just an aesthetic issue. These complex wiring harnesses are prone to failure points that are incredibly difficult to diagnose in real time. A single loose connection can bring down a whole zone, halting production for hours while technicians hunt through tangled bundles to find the fault. The solution lies in shifting from centralized point-to-point architectures to decentralized control using the Controller Area Network Protocol. This is an open standard known as ISO 1188 that was designed specifically for real-time communication between microcontrollers in harsh environments. By building a tiny zone controller on accessible hardware like an STM32 or teensy microcontroller, you can replace dozens of individual cables with a single twisted pair that daisy-chains multiple endpoints together. This architectural shift does not just clean up the floor, it fundamentally changes how your system scales and fails. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Here is where the engineering trade-offs become interesting. When you move to a CAN bus architecture for zoning, you are no longer relying on high-level operating systems with their unpredictable scheduling delays. Instead, you can implement deterministic latency directly in firmware using standard ISO protocols. This means that when a robot enters or leaves a zone, the switching happens with microsecond precision without being blocked by background processes. The controller logic becomes decoupled from the specific hardware it manages because the CAN bus acts as a universal language between your custom zoning algorithm and any motor driver you choose to plug in. This separation of concerns is what truly eliminates vendor lock-in. Because the core zoning logic runs on standardized communication protocols, you can swap out proprietary components for open-source alternatives without rewriting the entire control stack. You are no longer held hostage by a single manufacturer who decides when to discontinue support or raise licensing fees. The OpenAM robot ecosystem demonstrates this viability by providing production-ready firmware implementations that leverage these same principles. These open-source solutions prove that you do not need expensive proprietary stacks to achieve reliable, safety-critical operation in dynamic industrial settings. Now consider the concept of dynamic zoning itself as implemented on these custom controllers. In traditional centralized systems, zone management is often static or requires manual reprogramming when traffic patterns change. With a decentralized CAN-based approach, you can update zoning logic over the air to adapt to new floor layouts instantly. This capability mirrors algorithms like decentralized dynamic zoning, which have shown significant improvements in efficiency metrics within industrial environments. Research indicates that such dynamic approaches reduce travel distance standard deviation by 68.7% compared to static methods. That is a massive improvement in fleet throughput and energy usage, achieved not through better hardware but through smarter software architecture running on affordable microcontrollers. However, there is a critical reality check you must accept before building your own system. While the flexibility and cost savings are compelling, DIY implementations do come with performance trade-offs that commercial vendors absorb for their customers. The decentralized dynamic zoning algorithm shows improved task distribution, but initially exhibits lower throughput than fully centralized methods during complex production fluctuations. This suggests a learning curve where your custom controller may struggle to handle sudden spikes in demand until the software is fine-tuned through rigorous local testing. You cannot rely on standard validation data from commercial vendors because you are building something unique that requires its own safety guarantees and stress tests. The real value of this approach lies in the visibility it provides into network health. When a black box factory controller fails, you often have no idea why beyond a generic error code. With your custom firmware managing CAN bus arbitration and error frames manually, every failure mode is exposed to you directly in the log data. You can see exactly which node dropped out or where an electrical spike corrupted a message because of how you designed the protocol handling. This deep visibility allows for faster root cause analysis that simply does not exist with proprietary systems. It turns troubleshooting from a guessing game into a precise engineering exercise, giving your team control over system reliability rather than leaving it to vendor support tickets. Building this tiny zone controller is an investment in long-term autonomy and adaptability. You are trading the convenience of pre-validated commercial solutions for the ability to evolve with your production needs without external constraints. The reduction in cabling complexity by 60 to 80% alone justifies the effort, but the true payoff comes from owning your system's logic end-to-end. This approach empowers robotics engineers and entrepreneurs to build fleets that are not only cheaper to deploy initially, but also far more resilient to change over time. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.